Hello everybody and welcome to this new lesson in which we are going to find out why the hash table is indeed a frequency array on steroids and why every problem that can be solved using a frequency array can also be solved using a hash table and will be solved indeed using a hash table. So let's first find out what is a hash table. A hash table is just a collection of pairs that look like this: key and value. Now these two can be of any data type. The key can be an integer and the value also an integer, or the key can be a string maybe and the corresponding value an integer or a double or another string, right? So this is the first thing that makes the hash table more powerful than a frequency array, because in the frequency array, those keys could have been only integers, right? Remember, basically our keys were the values, were the indices I, and their values were their frequencies. So I and frequency of I, right? So I can't have an index, which is going to be a string, or I can't have an index 3.5. Frequency of 3.5 doesn't exist, right? So yeah, the hash table supports way more data types, but we are going to see that when solving problems. Now, one thing that is super powerful here is that you can access and modify the pairs of the hash table in constant time. This is interesting because the hash table is not stored in memory like an array. So it's not stored using a contiguous segment of memory. Those pairs are going to be stored in another way. Don't worry about the mechanics about it. We are going to have another video just on that. But you need to know that we are able to access and modify the pairs in constant time. So if, let's say, I know that I have some pair which has the key equal to 7, just knowing the value of the key, I can find the pair which has the key equal to 7 really quick, and I can even modify the value of the pair, right? So let's say it was 7, 3. I find the pair very fast in constant time, and I want to make it 7, 10 or something like that. I can do that also in constant time. You are going to see that this is super important. Now, let's think about what is the use case of a hash table. Well, usually when solving problems, the keys are the elements that we care about, and the values are their frequencies, right? So in most of the problems, we are using the hash table just to count the number of occurrences of something, right? Could be a string, could be an integer, could be a double. That's not important. For example, in the problem that we have just solved, remember that we needed to count for how many times each integer was present in the collection. So we basically had these pairs, I and frequency of I, meaning that the value I appears for a total of frequency of I times. These are going to be our key value pairs in the hash table. And yeah, this is exactly why I've taken an example, and we are going to go through it in order to see how the hash table changes during handling the events and how it corresponds to the frequency array. Again, let's suppose that our values were just digits, right? So it's not very complicated. We have initially the frequency array, which consists of 10 values equal to 0, as our collection is empty. And the corresponding hash table is going to be an empty collection. So I won't have any pair here. Now, let's say the boss calls me and tells me, hey, Andy, I want you to insert the value 6 into the collection right now. What I'm going to do? If I was to work with the frequency array, of course, I would have just incremented this value. So now frequency of 6 equals 1. What am I going to do in the hash table? Well, remember, these pairs mean that I have a value which is equal to the first element in the pair that appears for a total of the second value in the pair times in our collection. So I need to create a new pair that is going to suggest me that. What is the value? The value that we just added is 6. And for how many times does it appear? Of course, only once, right? So I'm just going to insert the pair 6, 1 into our hash table. Awesome. Now, let's say that the boss calls me again and wants, I don't know, to insert the value 3 in the hash table. Well, again, in the frequency array, I would have done this. Frequency of 3 now is 1. Here, I need to make a pair to actually suggest me that the value 3 now appears for 1 time in my hash table. And this is exactly what I'm going to do. I'm going to insert the pair 3, 1. Cool. Now, let's say that the boss asks me to count for how many times the value 0 appears in the hash table. This is super interesting. I'm going to look for a pair which has the key 0, right? So a pair who has the first element 0, and of course the second one, we don't know it, but we don't care about. We just care about the key 0. And I'm going to look. 6, 1, no. 3, 1, no. Okay, and the hash table is done. So I don't have any pair with that specific key. What does it mean? That that specific key wasn't ever inserted in the hash table. And yeah, basically it's not going to be in the collection. So I can say to the boss that the answer is 0. So the first difference between these two that I want you to notice is that when building the frequency array, I needed to have in memory one element for each possible value that is going to be eventually inserted in our collection. In the hash table, I don't need that. I can just look at the pairs, and if I don't have a pair with that specific key, I know that the answer is 0. This is awesome. Now, let's move on and say that the boss gives me another call and says, yo, Andy, I want you to insert again the value 6 into our collection. Well, in the frequency array, this would have become 2. But now, in the hash table, what should I do? I know that 6 is being inserted again in the hash table. So, should I maybe insert a new pair, 6, 1, in this hash table? Would have been a great way to do this? Well, no. And why is that? Because think about it. Why would I even store two pairs which have the same key when I could actually merge them, right? Having two pairs of 6, 1 means that actually the value 6 appears for a total of 2 times. So I can only have the pair 6, 2 to suggest me that. So one other rule that is very important and I need you to know about the hash table is that all the pairs in the hash table are going to have different keys. We will never have two pairs which actually share the same key, right? So I'm not gonna insert the pair 6, 1, but what I'm gonna do is that I'm going to look for a pair that has the key 6. So maybe 6 was already inserted in the past in the collection, and I find this pair. And remember, we can access and modify the pairs in constant time. So I can do this in constant time, transform this 1 into a 2. Now, let's continue. Let's say that the boss asks me, yeah, Wendy, for how many times does 6 appear in my collection? Well, again, in the frequency array, I would have taken a look at this element, but now in the hash table, I'm going to look for a pair which has the key 6. And of course, it is this one. And what I'm going to do, I'm going to return the second element in the pair, which is the frequency of that key. Cool. So I answer 2 and I move on. Let's say that the boss gives me another call and tells me, yeah, Wendy, you know what? I want you to remove the value 3 from my collection. So in the frequency array, of course, I would have decremented this. But now in the hash table, what am I going to do? If I have to remove a value, this means that that value is part of the collection. So if the value is part of the collection, I will definitely have some pair which will have the key equal to that value, right? So I'm going to look for a pair with key equals 3. And of course, I'm going to find it here. What do I need to do? Because I'm going to remove only one value of 3 from the collection, right? This, instead of 1, could have been a 3 maybe. Maybe there were 3 3s in the collection. You got the idea? I'm not going to delete the pair. That's not good. But what I'm going to do is that I'm going to decrement the counter. 3, 0, right? Then, after decrementing this counter, if the counter is equal to 0, then yes, I can say that, all right, I don't really need this pair anymore because it tells me that 3 doesn't appear in the hash table, so I can just delete it. Yeah, that's a valid thing you can do. It is not necessary. You can have pairs like this if you don't want to complicate yourself with making sure those pairs are deleted, and that will definitely work. Awesome. Now, let me make sure that I answer the question, why would we even use a hash table instead of frequency array? Well, this is very simple. Again, remember what I've told you. The frequency array is not a feasible option when those values could be huge. Let's say the maximum value that can be inserted into my collection is 10 to the power of 9, right? With a frequency array, I'm gonna need to have basically an element, right, for each of the indices from 0 to 10 to the power of 9. So I would need an array with 10 to the power of 9 plus 1 elements. And that is huge. And we definitely don't have memory for this. But in a hash table, I don't need to do that. And why is that? Because in a hash table, if some value was never inserted into my collection, then I don't need to have a pair for that value, right? If, for example, here 5 was never inserted into my collection. Do you see any pair that contains the key 5? No, we don't need that. And that is going to make our memory complexity dependent not on the maximum value, but on the number of events that take place. Think about what happens here. Initially, the frequency array already has a memory complexity of big O of 10 to the power of 9, while the hash table is empty, right? So constant memory. Then, when we deal with the events, when we have an insertion event, all we do in the hash table is either insert a new pair into that hash table or update an existing pair if that value was already present in our collection. When we deal with a removal event, all we need to do is take a look in the hash table, find the pair that contains a key equal to that value and decrement its counter. And of course, when we answer those questions, we just have to find the pair and return the frequency. So in the worst case scenario, where let's say we only have insertions, we are going to insert a new pair each time an event occurs, right? So let's say the boss tells me insert a 0. All right, I'm going to have the pair 0, 1. The boss tells me insert a 1. I'm going to have the pair 1, 1. The boss tells me insert a 2. I'm going to have the pair 2, 1. And so on and so forth, right? Until I exhaust the number of events. And let's say on the last event, the boss tells me to, I don't know, insert the value 10 to the power of 5 into the collection. So I will insert a new pair here. So what happens here is that even if the elements can be as large as 10 to the power of 9, my number of pairs in the hash table will be at most 10 to the power of 5, which is the number of events. So the time complexity that a hash table has is dependent on the number of events. And we can say it is big O of, I don't know, let's call it number of events. This is beautiful. Imagine the problems that you are going to solve in the future. For those problems, maybe you will deal with values as big as 10 to the power of 9. That is definitely a feasible scenario, but you will never be given a number of events which is such big as 10 to the power of 9. Because think about it, it will take a lot only to read those events. So in most of the problems, you might have big values, but the number of events is going to be a decent one. So when you do the hash table, the memory complexity of our approach is going to be a decent one. And this is how we can solve the problem. Awesome. So we have seen what a hash table is. We have seen how a hash table works, right, in the context of some problem. And all that is left to do is see how the code looks like. You are going to be very impressed because every language has this data structure implemented. So it's going to be very easy to write the code for it. And in fact, you are going to see that it's 99% identical to the code that used the frequency array. So let's look at the code. All right. And here is the code. So the first thing that I do is that I declare my hash table, which will be named number of occurrences and is initially empty. You might notice that here I've written hash table or dictionary because it depends on the language, right? In JavaScript and Python, this is actually called a dictionary, and you can define it just by, I don't know, let number of occurrences equals this. But in other languages like C++ or Java, you are going to write it a little bit different. For example, in C++, a hash table is an unordered map, and in Java, you're going to create a new hash map for that. So let's take a look at the functions. The first function is insert a val, and as you can see, the syntax is beautiful. It is just like the frequency array. In most languages, you can use a hash table just like you use a normal array. So I say number of occurrences of val plus equals 1. And what I want to do now is break this line of code into the two operations that happen here. We have the first operation, which is number of occurrences of val. And this is actually an access, right? When you write it like this, the program is trying to access the pair in the hash table that has the key val. So I obviously have two possible scenarios here. The first one is when I really have a pair with the key val into my hash table. So let's say I have the key val and the second argument is x. Let's call it x, doesn't matter. What's going to happen is that it's going to find the pair and it's going to access it. Now, the second operation plus equals 1, the program is going to know that, all right, what you are trying to do is modify the second argument of the pair because this is the only one that can be modified. The key cannot be modified. You're trying to modify this. So what I'm going to do is, of course, convert this pair from val x to val x plus 1. Everything happens in place. and in constant time. Cool. Now, we also have the second scenario here in which maybe I try to access the pair that has the key val, but I don't have any pair that has the key val. The program is smart. And what it does is, if it doesn't find any pair with this key, then it is automatically going to create one. So it doesn't find any. So what's going to do is create a new pair with the key val. And this is the interesting part. What's going to be the second value, right? The second value is going to be the default value of that specific data type. So for example, if you have a hash table that consists of pairs of integer and integer, like in our example, right? What's going to do is that it's going to create a pair with the val that you basically try to access and with the default value of the data type integer, which is of course 0. So it's going to create and insert in our hash table the pair val 0. So now it exists and we can access it. And what's going to happen next is that it's going to increment the second argument and it's going to convert it into val 1. So be very careful. This is what happens behind the scenes. And this is exactly what we want in this type of scenario, right? If this is the first time that we insert the value val into our collection, we will expect to have a pair val 1 into the hash table. Cool. Now let's take a look at the removal function. Again, the same two things happen here. First, we are looking for the pair that has this key equal to val. And here we are actually guaranteed that we are going to find one because we are never going to remove an element which is not part of the collection, right? So we will always have a pair with this key in the collection. We find the pair and of course we decrement its frequency. And then the third and the last function is counting for how many times the value occurs in the collection. First of all, I'm asking the hash table if it contains a pair with this key equal to val. And if it does, I can return the number of occurrences or the second argument of that pair. If it doesn't, of course, I'm going to return 0 and that's it. One other thing that is worth mentioning here is that I could have written this code without these two lines. I could have just written return number of occurrences of val. And why is that? Because, again, the two scenarios. If I have a pair with this key, I'm going to find it and return the frequency. If I don't, the algorithm is going to create one for me and is going to return the frequency, which is 0. And 0 is indeed the right answer. So I could have done this. But the beautiful part about this whole code is that I'm not creating pairs that maybe I'm not going to ever use, right? So I don't know if I create the pair val 0, if it is actually going to be ever used. So it is safer to do this kind of approach in which you don't create unnecessary pairs, but it is also correct to just return the number of occurrences of val. Awesome. This is it, guys. I hope you really understood the hash table. Again, don't worry about the mechanics behind it. We are going to take a look into that later. But for now, I need you to know that all the problems that can be solved with a frequency array can also be solved with a hash table. The hash table solves the memory problem that the frequency array has and is also way more powerful because these keys can not only be integers. We are going to see that we will need to count how many strings are there in a collection, how many doubles, and you can't do that with a frequency array. And also accessing and modifying the pairs inside the hash table happens in constant time, right? So all of these three functions are going to be executed in constant time, and also just declaring the hash table or the dictionary at first, which is empty, is also constant time. Awesome, guys. I hope you enjoyed it, and I'll see you in the next one. Bye.